the last one will be a kind of an invitation to various advanced topics, one, the Pontryagin classes, and then also more contemporary work and even open questions. Today I wanted to talk about a sort of a classical, so to speak, application of characteristic classes, namely, and this is one near and dear to my heart, which is Bordism theory. So we say that M1 is cobordant to M2. I won't necessarily say cob all the time. If there exists a W, so that the boundary of W is diffeomorphic to M1 disjoint union M2, and well, that's the most vanilla flavor. We can say that if so here all the MIs and the W's are smooth. If MIs are either oriented or let me call it weakly complex, that just means that they're tangent bundles, or really we'll need the stable normal bundles to be complex. Let me make this a little bit bigger. Then what we can do, then we say that this we demand that at one side the natural boundary will the orientation on the tangent bundle of W is going to induce orientations on the tangent bundles of both ends, and you have that in one case you get the reversed orientation. Or the opposite complex structure. Right. This makes sense, by the way, in the weakly complex setting, because you don't need to be an even dimensional manifold to be weakly complex. In the case for odd dimensional manifolds, you're allowing yourself to add a trivial bundle to the tangent bundle and get something with a complex structure on it. Again, nothing complex means nothing like holomorphic. So this is a cruder equivalence relation than diffeomorphism. If two manifolds are diffeomorphic, they're cobordant, M cross I being a perfectly good cobordism, for example. And it seems to be, it is in fact distinct from homotopy equivalence or even homeomorphism. But it's hard to tell a priori how hard this is going to be. Well, I guess it's simple enough. So these flavors we call omega O star, or sometimes, since it's vanilla, we're not demanding anything on the tangent bundle, we just call it omega star. Oriented is often omega SO star. This weakly complex is omega U star, and you can imagine others. And it's fairly clear to see that in all cases, omega whatever star sub 0 is either, well, Z in the oriented cases or Z mod 2 in omega, the unoriented case, because if you have two zero manifolds, they're union. So by the way, you allow M1 or 2, M2 can be empty. So let me even redraw this. If I take two zero manifolds, that's a cobordism drawing there to the empty set. So that's in particular everything which is 0. These isomorphisms are as abelian groups. So exercise, these are all rings Addition is through disjoint union. We didn't say anybody had to be connected. In fact, in some cases, you find that, I'll draw it up here. Here's a cobordism between some one manifolds, right? And going, so properties such as connectivity obviously are not being preserved under cobordism. So addition is disjoint union. I'll let you figure out what inverses are. Multiplication is Cartesian product. So this is a great little exercise. And you can also then see that whatever all these flavors in degree 1 are all 0 because this one manifold, I'll give you a cobordism to the empty set there, right? So it bounds a disk. Maybe I'll even just draw it as bounding a disk. Sorry, a little. I'm having technical problems. There we go. Sorry about that. So anyways, we've got this one manifold and it bounds a disk. Great. And then, but it's not clear, when we no longer have so few manifolds, how this works out. So let me just tell you that, for example, omega 2 in the standard theory is not 0 because I claim that RP2 is not the boundary of any W, which is three-dimensional. Why? Well, if it were, I could take two copies of that W. I'm going to use a tubular or collar neighborhood theorem to make this smooth 3-manifold. And this smooth 3-manifold will have Euler characteristic equal to twice the Euler characteristic of this W plus the Euler characteristic of RP2, or maybe I should say minus. But the point is, which is congruent to 1 mod 2, which is not 0, but the Euler characteristic of a 3-manifold without boundary, and this double construction is a 3-manifold without boundary, by Poincare duality has to be 0. So this is not 0 because the class of RP2 is not 0. So that's an ad hoc argument, and then you might want to have a more systematic way to tell Bordism classes apart. And in fact, the machinery that we've set up and the perspective that we have are perfectly suited for that. So in fact, we can define, something from the unoriented Bordism ring to the nth homology of the Grassmannian of n planes in R infinity, say, with z mod 2 coefficients. Or similarly, from the complex, weakly complex Bordism in degree 2n to H2n of the Grassmannian of n planes in C infinity. And that's integer coefficients, by taking the equivalence class of M to I'm going to use a classifying map for the tangent bundle of M and apply it on homology to the fundamental class of M. So these are two different bracket M's. This is on the left, it's an equivalence class represented by M, which is cobordism. On the right is this traditional way we talk about a particular class in the homology of M and its top homology. If we're oriented, we use that orientation to choose plus or minus one. If we're unoriented, it doesn't matter. So yeah, and then the point is that this is well defined. I'll just draw a picture. Because if N is cobordant to M through some W, then the tangent bundle of W, so let's look at the classifying map of the tangent bundle of W in homology is going to give us a relative class. It's going to give us a homology, in fact, between, so maybe I should really just say sharp here at the chain level is going to give us a homology between their fundamental classes. Between the fundamental class of M and that of N. So, that's our main construction, and quote unquote, this is this image. So this homology class is the invariant, the characteristic number invariant. So the claim is that characteristic numbers encoded. So the invariant is this homology class in the homology of a Grassmannian. So given a manifold, I can make a homology class in the Grassmannian because a manifold has this tangent bundle, this God-given tangent bundle. That tangent bundle gives you a map to a Grassmannian. The manifold also has a God-given homology class associated to it, the sum of all the top dimensional simplices. And I can look at the image of that in the Grassmannian. So all this data fits together. And characteristic numbers encode it because, well, if I wanted to, we're either over or mod 2 or in the complex setting where we're sort of torsion free. So if I take some sort of monomial in characteristic classes, some product of Stiefel-Whitney classes, W1 squared times W3 or something like that, and I evaluate it on the classifying map of the tangent bundle of M on the fundamental class of M, then by naturality, because this is the image in homology, I could instead pull back the cohomology classes, but pulling back the cohomology classes, again, this is in the cohomology of GRN R or C infinity. Pulling back those cohomology classes, those are exactly the Stiefel-Whitney or Chern classes of the tangent bundle of M, and those are evaluated on the fundamental class of M. And this, if you run through, this is gives a proof that those characteristic numbers are invariant. Typically, you use some sort of long exact sequence of or use the compatibility of these fundamental classes and a relative fundamental class for a manifold with boundary, and that's what I was sort of sketching above with the cobordism W between M and N, giving rise to, if I choose, say, a triangulation of all of those, giving rise to a way to compare the fundamental class of M and the fundamental class of N. Okay, so so then here's a little exercise or a big exercise. We can even think of this as a final exam for this class. For our ideas, make sure you can calculate some things. So exercise, show that if I look at RPI for I not one less than a power of 2, those, remember, have no interesting characteristic classes of their normal bundles, that this is actually a polynomial subring. In other words, there's no relations of the standard Bordism. And same for, and here we have no dimensional restrictions. And this is over the integers in the complex setting. Let me just, since I was very brief in that these characteristic numbers, first of all, they're just defined. We can think of them inside the homology of a Grassmannian, but we can pull back to do these calculations. So let me just give you a quick example. In fact, I'm not even 100% sure. So I'm not allowed, RP1 is out, which is good. The circle bounds of disks. I've got RP2 and RP4. So you can look in the fourth Bordism at these four manifolds. And the claim is that there's no relations between them, no linear combination of those, which is 0. In other words, this is over the field with 2 elements. They aren't equal, or one of them isn't 0. And what I can do is look at the characteristic classes, W1 taken to the 4th power. That's what I need to do in order to evaluate on the fundamental class in degree 4. By the way, we often by abuse just say characteristic classes Wi, but in fact you really want to say that all polynomials in in the Wi's, all polynomials in the CI's are themselves characteristic classes. They're natural and the whole 9 yards. So it's standard abuse to sometimes only refer to the generators, but really, especially for this exercise, you want the full ring. So W1 of RP4 is not orientable. Little exercise, I don't know if we've even mentioned this, is that then the W1 is 0 if and only if a bundle is orientable. Since this is not orientable, that's non-zero. That's a non-zero class in H1 of RP4. If I raise it to the 4th power, that's a generator. Whereas I can now W1 of the, well, I mean, the point is that W1 to the 4th, even if it was, say, it is X1 plus X2, but if I raise those to the 4th, well, I get all even numbers for my coefficients. I also get powers of things greater than 2. And so I get 0 here. W2 of RP4, well, RP4 is, its tangent bundle has the same characteristic classes as a direct sum of 5 tautological line bundles up until the last degree. So I look at I look at Pascal's triangle, 1, 5, 10, 10, 5, 1, because 10 is even, W2 is 0, so this is 0. Whereas W2 of RP2 cross RP2, I am going to have a, let's see, I'm both going to have that sort of X1 plus X2, the generators, that squares, that's good. Otherwise, I also do have a W2, I'm thinking of the Whitney sum formula. Oh, right. Well, the X1 plus X2 squared is 0, but again, let's call it an examples exercise to check me. I think these are correct. But this is then what you have to do in any degree. So you have to get yourself a bit organized about all these binomial coefficients that show up. CPI might even be better to do first. And a warning there, what we have, let me sort of say something about this. So though S2 is the boundary of D3, this doesn't happen compatibly with one of these weakly complex structure on the tangent bundle of D3. So your calculations there includes things like CP1 is S2, and you might be surprised because S2 is 0 in the oriented Bordism ring, omega SO, but it's non-zero in omega U when you give it the weakly complex structure natural as just CP1. And yeah, that takes a little getting used to. Okay, so I wanted to, so we know that these equivalence classes, if you do these exercises, they're kind of at least a somewhat large, interesting set. But why do we know that it's manageable at all? Well, that was this wonderful work of Renee Thom. So in fact, it's a Goldilocks theory. These are equivalence classes because diffeomorphism on manifolds is, or homeomorphism for that matter, because of the fundamental group, it can't be algorithmic, right? This is a standard fact. And so starting with those diffeomorphism classes, you've got sort of a too large a set in some sense to, or at least too subtly encoded for many applications. And so it's nice to say only look up to homotopy equivalence or something like cobordism, but you don't want to quotient down to nothing. So the point is that these equivalence relations are kind of a Goldilocks equivalence relation, if you're familiar with that story from American childhood anyways, that's somewhere right in the middle. There's enough structure there to get some interesting, to see some interesting phenomenon, but not too much that you're sort of overwhelmed. So what's the theory, what's the story there? There's something called the Pontryagin-Thom construction. And I'm just going to tell it in stages. This is going to be a sketch. There's an invitation. It really starts with Hopf, who I think Hopf fully understood this, that, well, he was certainly the first to look at higher homotopy groups and realize there was something interesting there. And what you can follow from Hopf is that I think this was Hopf and doesn't first realize that Pontryagin wasn't the first to observe this in this case, that maps from S3 to S2 up to homotopy are in one-to-one correspondence with one manifolds framed one manifolds in S3 up to cobordism in S3 cross I. Okay, and how does this go? So what you can do this way is you send F goes to, I'm going to look at the pre-image of 0, you know, say, or pre-image of infinity maybe on S2. I've got S2, and this is 0, and this is infinity. And I like to base things at 0, so that means I want to maybe take the pre-image of infinity. And that is going to be if f is transverse, so you have to play some games here. There's a lot of details, but any f is homotopic to one which is transverse to infinity. And then f inverse of infinity will be some one manifold. And general differential topology that we've talked about before, the tangent bundle, the normal bundle to infinity is going to pull back to the normal bundle here, but that means that I've got everywhere, I've got some sort of framing, and that can actually twist around as it does for the Hopf map that we talked twice ago. That framing twist is exactly 1. Is it 1 or minus 1? I think it's 1. Great. And how does this go the other way? If I have a framed one manifold, call it M inside S3, if it's framed, what I'm going to do is I'm going to collapse, and that's going to give me a map from S3 to the tome space of the normal bundle of M. But the normal bundle is trivial, and so then I can take each of those fibers. That tome space admits a projection to S2, and so I get a map from S3 to S2. Okay, so this is let me draw just a little bit, do my best. So M is this framed one manifold. Doesn't have to be connected, but I'll view it as connected. And maybe the framing twists as we go around. And what you can think about that as telling us is that at every fiber, I've got a disk that use a tubular neighborhood theorem to say at every fiber I've got a disk. So I've got a standard map to the disk. This disk can map to the two-sphere. And everything, maybe I should have switched the roles of 0 and infinity, because we often think about if I collapse the disk, yeah, I should have said F inverse of 0. Let's do that. Because it's more natural to collapse everything in the boundary of the disk that becomes a point at infinity. So each of these disks has a natural map to S2. Zero is going to the base point, and then the points at the boundary of the disk are going to infinity. So in fact, each one of these purple points at the center are going to 0. And then what happens is outside, everywhere in green, is also going to go to infinity. Because in fact, once every boundary of the disk goes to infinity, it's immediate, some sort of gluing theorem from points at topology that I'm free to just map the rest of S3 to the point at infinity. Okay. And you want to show that these are inverse to one another. Again, I will not go through those kinds of things. This is just an invitation to some further work. But then what I want to say is sort of next on this list is that we can look at there's nothing special about 2 and 3 here that maps from S in plus D to S in up to homotopy are in one-to-one correspondence with D manifolds, framed D manifolds in S in up to cobordisms in S n cross I. Because by the way, I just gave the maps. The fact that they're inverse to one another at some point, well, we even need to show that they're well defined here. And the point is, let's look at the easier direction, take an F and look at F inverse of 0. If I have a homotopy between F and G, I can call it H. I can look at H inverse of 0. And lo and behold, under transversality, that provides a cobordism between F inverse of 0 and G inverse of 0. So cobordism is a natural equivalence relation when we look at preimages and we're doing homotopy, but it's cobordism in the domain space, domain manifold cross the interval. Okay, so this was Pontryagin who realized this, and he tried to use it, and he did use it to make some calculations in homotopy groups of spheres. But then where Thom comes in, well, what we want is to get rid of the framed. And maybe put oriented or something like that, or nothing at all. But I just suppose I want to just look at D manifolds in S in plus D is how I'm going to do that. Oh, this was S n plus D here. Sorry about that. Because that was the domain. That's where everything's happening in Sn plus D. So I'm going to look at D manifolds in Sn plus D. Forget about the framing, and then look at them up to cobordism in Sn plus D cross I. And then if I let n go to infinity, I recover omega D or omega whatever, omega O or omega U or omega SO. The reason being that if I any manifold embeds by the Whitney embedding theorem in a sufficiently large manifold, then any cobordism would embed eventually in a sufficiently large manifold as well. So, in order to account for the lack of framing, the non-triviality of the normal bundle, Thom realized that instead of mapping to, well, the sphere is a Thom space of a trivial bundle, if you want to capture any normal bundle is what you actually want here, not the tangent bundle, then you're going to look at maps from Sn plus D to the Thom space of a tautological bundle over a Grassmannian. So this is one of the things that Thom proved. the proof relies on the fact that the normal bundle, you take your W, and you go to, you define a map from S in plus D. First, you collapse onto the tome space of the normal bundle of W. And then that has some classifying map to this gamma, universal gamma N. And so that's how you translate from cobordism to homotopy of some space. And in the other direction, you're going to go from F to the preimage of the zero section in this tome space. And those end up being reverse. So, so the geometry is very similar to what we talked about for the three-sphere to two-sphere case. The main thing being that we use the fact that Grassmannians are universal for bundles, and since we don't have the framed condition, what we do is classify the normal bundle of the of our manifold in S n plus D. Again, we're going to let n go to infinity, but we're going to still have these D manifolds. So remarkably, these homotopy groups, and maybe I'll come back to that in a second, are so right. This is another way to say the N plus D homotopy group of this tome space. And again, we might want to take the direct limit over N, and then Tome's theorem is that this, in this case, without any orientations or whatever, what you get is omega D. Okay, so let me say a little bit more about it, because we just talked about characteristic numbers, and what we said is that let's look at this. Let's look here. If I'm given a manifold, let's call this the F sub W. And let's understand the impact of F sub W on homology. Right, so I'm going to go from Sn plus D. I'm collapsing into the, again, to this tome space. Right. If I'm thinking about homology, this ends up being an isomorphism in the degree, in the only degree of interest, N plus D. So in fact, let's keep track that there's only one degree of interest here, namely a degree N plus D. So if I look at the N plus D homology, of the tome space of the normal bundle of M, it ends up being that this is an isomorphism. The reason being that this is isomorphic, and there's, I don't know which way we want to write the map, but this is isomorphic to the top homology of M under the tome isomorphism theorem. Okay? So that's the first thing we do is we collapse on the tome space of the normal bundle. The next thing we do is just map the tome space of the normal bundle to the tome space of gamma n. Again, I'm just going to focus on Hn plus d of the tome space of gamma n over the Grassmannian. But of course, there's also a tome isomorphism over here that Hd of the Grassmannian of n planes in R n plus d. And here I've got my classifying map of the normal bundle. I claim that this commutes, and so we see that the image of F on homology is encoding the image of the fundamental class of M. So the fundamental class of M goes to the, these are all Z, by the way. So this is Z generated by the fundamental class of Sn plus D. Here's Z generated by the fundamental class of M. This is also Z, and these are all compatible. And so the image of this F sub W through Pontryagin tome collapse is encoding the image of the fundamental class of M under the classifying map of the normal bundle. Okay, so there's a little distinction here. I told you about characteristic classes of the tangent bundle. Tome's theory says that we should perhaps really be looking at characteristic classes of the normal bundle. These encode each other. So in some sense, we're not losing any information. We've got equivalent information between the two. But this is a fun little diagram which relates this different perspective on characteristic numbers. In other words, characteristic numbers are, so this homomorphism, again, is just sort of normal bundle characteristic numbers. And those normal bundle characteristic numbers are essentially then, what they're doing is going from, if you think about it in Tome's theorem, over here, instead of homotopy of this space, I could look at homology. And this is a Hurewicz map. And so what the characteristic numbers are telling me is about the Hurewicz map for some space, or really it's, I've got this limit here. So yeah, so that's sort of another way to understand both, maybe not understand any better what characteristic numbers are, but understand their connection to Tome's theory. And it's lovely that it's just this Hurewicz map. Right. In fact, there's so much more to say here. Bordism theories are generalized homology theories. They're represented by objects called spectra. These omega stars are all homotopy groups of these spectra. So you have things like omega O is, this object is often called pi star MO. So there's some object MO whose homotopy is this direct limit. It's pre-spectrum actually, I guess, and if I want to give its homotopy as a direct limit, but well, or I could spectrify and I'd still see the same direct limit. Um, so again, these characteristic numbers all encode Hurevich homomorphisms. They don't always detect all forms of Bortism. Even when they do, even when they're injective, there might be, you might have like, they're always divisible by 2 or something, so they're not efficiently injective, but that's plenty of classical mathematics. And believe it or not, such calculations, so what Thom found is that the cohomology of these spaces, these Thom spaces, in, in the first case, they became free over the Steenrod algebra, which meant that when I looked at the maps which classify cohomology to a product of Eilenberg-MacLane spaces, that's an equivalence. So you can determine homotopy from homology. The remarkable thing about these Thom spaces in general is that their cohomology tends not to be very far from free over the Steenrod algebra. So something called the atom spectral sequence is remarkably effective. And there's a lovely survey paper by Agnès Baudry and Jonathan Campbell about such calculations, which come up in very recent lattice models and field theories. So various things. So somehow this initial picture of this pair of pants cobordism, which I'll maybe draw to the left here again, just to remind you, you can think about that as sort of as some way to take one manifolds, and you'll notice that if I'm thinking about this sort of maybe with a Morse function or something on it, then exactly once I'm the one manifolds fuse together, and these kinds of cobordism calculations with tangential and not normal data, interestingly. The classical cobordism theory was all from Thom. You point out the primacy of the normal bundle, and the naturality of the tangent bundle becomes kind of a secondary thing, and the information is there in both. In modern cobordism categories, field theory kind of applications, the tangent bundle actually plays the entire role. The normal bundle, I think, is nowhere to be seen, if I'm not mistaken. But interestingly, these calculations are coming back again in physics.